Hello guys, so we will be starting a new topic today, that is ionic equilibrium. It is a topic of the chapter 11th class NCERT chemistry chapter equilibrium. So let's start. What is ionic equilibrium? In ionic equilibrium, ions are involved. It is an equilibrium which involves ions in an aqueous solution. So what are the different ions that can be present in a solution? They can be electrolytes, non-electrolytes. Okay, what are electrolytes? Now electrolytes are those which can conduct electricity in a solution, whereas non-electrolytes, they cannot conduct. So electrolytes, they can also further be classified into strong and weak electrolytes. Strong electrolytes on dissolution in water are ionized completely, while the weak electrolytes are only partially dissociated. So this is the difference between strong and weak electrolytes. Some examples of strong electrolytes are sodium chloride, and non-electrolyte which doesn't conduct electricity is glucose. Okay, and acids, bases and salts, these three are the main three electrolytes that we'll be considering in detail in this chapter. So let's start with Arrhenius concept of acids and bases. So according to Arrhenius, acids are the substances that dissociates in water to give a H+ ion or the hydronium ion, and bases are the substances that produce hydroxyl ions. Hydroxyl ions are OH- ions. So this happens in water. If this is an acid, HX, or you can consider X as in halogen, or halogen can be chlorine, bromine. So if this is HCl in water, it will dissociate to give H+ ion or hydronium ion, and then X- or a halide ion. So this is an H+ ion, whereas in base it will dissociate to give us an hydroxide ion. So this is the basic theory which says that acids gives H+ ions and bases give hydroxide ions. So we can show H+ ions like H+ or like H3O+. Since the H+ ion is very reactive, it cannot exist freely in aqueous solutions. So thus it can bind to the oxygen atom of the solvent or the water molecule to give us the trigonal pyramidal hydronium ion. Okay, so this H+, it will attack the oxygen of water molecule to give us the trigonal pyramidal hydronium ion. So this is basically more correct way of representing a H+ ion. So now this theory has certain limitation. That's why we do not define acids and bases according to Arrhenius. The limitation was that limitation that it is applicable only to aqueous solutions. So we cannot tell a substance is acid or a base until and unless we see its behavior in water or in aqueous media. So this is certain big limitation. And we all know that ammonia, NH3, is basic, but this ammonia NH3 group, it does not possesses a hydroxyl group, OH- group, hydroxyl group. So how we can now tell that it's base or not? This possesses the difficulty. So to counteract all these limitations, another theory came. That was the second one, is Bronsted Lowry acid and bases theory. So according to Bronsted Lowry acid and base theory, an acid is a substance that is capable of donating a H+ or a hydronium ion, whereas a base is a substance that is capable of accepting a H+ ion. So this is main theory. So if we consider the dissolution of ammonia, if we consider this equilibria, NH3 in water, the equilibrium takes place. NH3 will take one proton from water and will become NH4 ion, and H2O has donated one H plus ion to NH3 and it now becomes OH minus ion. So in this equilibrium we can say that acid, which is water here, and the base is ammonia. Acid has donated a H plus ion to ammonia, so it's an acid, and the base has accepted a H plus ion. So this is one thing. One important thing that I want to tell you is that acid, that water molecule, it can act as both acid and bases. If it's present with the base, it behaves like an acid, and if an acid was present in place of base, it would act as a base. So it possesses dual character, both base as well as an acid. So a base, on addition of a proton, it will form a conjugate acid. So you say that base will form a acid, conjugate acid, and an acid which has donated a proton will become base, and that is a conjugate base. So we have to remember, base will become acid, conjugate acid, and acid will become base, and more importantly, more precisely, conjugate base. So why we say what is a conjugate acid base pair? So conjugate acid base pair, that is, if we consider this equilibrium, ammonium and hydroxyl ion, this acid base pair is called a conjugate acid base pair if and only if it differs by one proton. We see that this has got one proton and this has got one less proton. So we see from the reactant side that both these initial reactants, these differ by one proton. Okay, so this is another equilibrium. Here we have taken an acid, HCl. Now, as I told you that water can act as both acid and base. So if acid is present here, it behaves like a base. What is the property of a base? That it will accept the H plus ion, and acid will give an H plus ion in aqueous solution. So this water molecule will accept a proton, become H3O plus ion, and this HCl loses one proton to form the chloride ion. So acid forms a conjugate base and the base forms a conjugate acid. So you always remember, base will form a conjugate acid and acid will form a conjugate base. So this was all about the Bronsted Lowry acid basis theory. So another important term that we have to see here is Bronsted acid. What is a Bronsted acid? Bronsted acid is actually a strong acid. Bronsted term refers to strong, strongness, strength. Okay, if this is a strong acid, then its conjugate base is a weak base and vice versa. Okay, so if you have a strong base, we will have a weak conjugate acid. See, we have a strong base, ammonia, and the conjugate acid is a weak one. Or we can say that if we have a strong acid, HCl, the conjugate base is a weaker one here. So this type of question comes in exam. If we have two acids, H2SO4 and HF, we have to write the conjugate base for the following Bronsted acid. As I told you, Bronsted acid is a strong acid. So these H2SO4 and HF are strong acids. So we have to make a conjugate base for the acid, which is now a conjugate base. Acid will donate a proton, so it will form, for H2SO4, the conjugate base will be HSO4 minus, and for HF, the Bronsted, for this Bronsted acid, conjugate base will be fluoride ion. So it's very simple. For this second one, we have NH2 minus, and for an HCO minus, we have to write the conjugate acid for the following Bronsted bases. So these are Bronsted bases. If the Bronsted base is weak, then the conjugate acid will be stronger. Okay, so what is a a conjugate acid. Conjugate acid is something which has accepted a proton. So for NH2 minus, it will become conjugate acid. Shows reverse properties of an acid. According to Bronsted-Lowry theory, conjugate acid, according to Bronsted-Lowry theory, the acid should actually donate a proton, but the conjugate acid accepts a proton. Here NH2 minus accepts a proton to form NH3, and HCOO minus will form HCOOH, that is your formic acid, after accepting a proton. So it's formed. It forms a conjugate acid as it has showing opposite or reverse properties of acid. So that's the meaning of conjugate. Now the third theory is Lewis acids and bases theory. Now Lewis acid and bases theory, how will you remember these all three theories? Like what actually the definition they gave about acids and bases. If you remember first two, the trick for remembering third one is, as we have you will have studied about Lewis electron dot structures that we drew to understand bonding between the atoms, chemical bonding between the atoms. So in that Lewis electron dot structures we show electrons. So this theory is also based upon electrons. So according to this theory, acid is a species or a substance which accepts an electron pair. Whereas a base is a species which donates an electron pair. So we must have also understand that the electron and a proton. Proton is H plus and electron are minus charged species. So in the Bronsted-Lowry theory, we studied that acid is a species which donates a proton. So here it will accept an electron pair. And similarly for base, there a base would accept a proton or hydronium ion, H plus ion. Here it will donate an electron pair. So this is actually vice versa, reverse of the Bronsted-Lowry theory. So we will see an example of Lewis acid and base theory. We have this BF3 and this ammonia. Now this BF3 is an acid. Now we will ask how it is an acid if it doesn't possess a proton or an H plus ion to donate. So we say that it is an acid despite it does not have a proton. If this is an acid and this is ammonia molecule, it has a lone pair of electron, it's a base, and this is an acid. Now we study that acid will accept an electron pair. So here we can show that BF3 and ammonia, this is the electron pair that has been accepted by BF3. So this is also another way of defining acids and bases. Now what are the different possible types of Lewis acids? Lewis acids, this AlCl3, aluminium chloride, aluminium has 3 electrons in this outermost valence shell, so it is electron deficient, and it's electron deficient, so it is an acid. Similarly, cobalt 3 plus and magnesium 2 plus. Lewis base are something which possess an electron pair to donate. This ammonia molecule has an electron pair, as we have seen here. Hydroxide ion, so you have seen that this has a minus ion. A minus ion generally means it has 2 electrons, so that's why it's a Lewis base. Similarly, water molecule, you have seen that water has 2 lone pair of electrons to donate, that's why it's a Lewis base. So this one point is important point is to remember that strong acids have very weak conjugate bases. The same point we have studied back only. Strong acids have very weak conjugate bases and vice versa. If the acid is weak, the conjugate base is going to be very, very strong. Let's now come to another topic. ionization constant of water and its ionic product. So here in this chapter we are now referring to all the theory material. I am doing a little bit of questions that I thought are that it's easy and I can cover in the theory part. So we are now doing ionization constant of water. If we consider this equilibrium, we have water and another one water molecule. Now if this water molecule behaves as acid, this will be behaving as a base. Now acid will accept a proton. Acid will donate a proton to form a conjugate base, and the base will accept a proton to form a conjugate acid. Same thing that I have told you in the Bronsted Lowry acid base theory. So if we write K, the dissociation constant for this reaction, we can write dissociation constant, we write only the ions, aqueous form, which are in aqueous form, not the pure liquid ones. So dissociation constant is written as H3O plus Ironium ion. The react product ones come on the top, followed by divided by the reactants. Hydronium ion, OH minus divided by water molecule. Since we know that in equilibrium constant we do not write pure liquids or solids, we write only ones which one are dissociated or ionized form. So water, concentration of water will be omitted because it's a pure liquid. So now this dissociation constant, after omitting water molecule, it becomes Kw. It's called Kw is ionic product of water. It becomes equals to H3O plus multiplied by OH minus. So this is ionic product of water. So experimentally we have found out that concentration of hydronium ion, H plus ions or H3O plus ions, whatever you like to call it, is 1 into 10 raised to the minus 7 molar or moles per liter at room temperature 25 degrees Celsius or 298 Kelvin. So we also know that water molecule, it dissociates equally into equal number of moles into H plus ions and hydroxyl ions. So concentration of H plus ions is equals to concentration of hydroxyl ions. So Kw, ionic product, becomes equal to the product of concentrations of H plus and hydroxyl ions. It becomes equals to 10 raised to the minus 14 molar square. So now Kw is temperature dependent. Since ionic product is an equilibrium constant, the concentration of H plus and OH minus ions is nature dependent, hence ionic product is also temperature dependent. So next topic is pH scale. What is now pH scale? You all must be knowing it till now that pH is the negative logarithm of the concentration of hydronium ion, H plus ions. So pH is negative logarithm of the activity of hydrogen ion. Of the activity of hydrogen ion. Now the activity of hydrogen ion is equal to concentration of H plus ions only per mole per liter. Hence the concentration units are mole per liter. Activity is given as concentration of H plus per mole per liter. Hence we can say that activity has no unit. It is unitless. So we can write pH is minus logarithm of activity of H plus ions, or it is also written as minus log of concentration of H plus per mole per liter, because activity is unitless. So if you have to find out the pH of an acidic solution of HCl, what is the pH of an acidic solution of HCl whose concentration of H plus ions is 10⁻⁻2 molar? So we'll use the formula pH is equals to minus log of H plus equals to minus log of 10⁻⁻2 equals to 2. So pH comes out to be 2. Also, you must be knowing that pH of acidic solutions are lower than 7. For basic solution, the pH should be greater than 7. For a neutral solution, the pH should be equals to 7. Now this is another question from the 11th Ionic equilibria NCERT. The basic solution of NaOH. Now this is a basic solution, and we are asked to find out the pH. Having hydroxide ion concentration as 10⁻⁻4 molar and H plus ion or hydronium ion concentration as 10⁻⁻10 molar. So don't get confused. We only have to use the H plus ion hydronium ion concentration for calculating the pH. So we will use only this value and not this. If we were asked to calculate pOH, then we would use this value. So for calculating pH, we have minus log of H plus becomes equals to minus log of 10⁻⁻10. So log will bring the power in front and becomes minus of minus 10 log 10. Since log 10 value is 1, answer comes out to be minus minus plus. So this is the pH of a basic solution. Quite true, because basic solutions have a pH greater than 7. So this is again acidic solution pH, basic solution and neutral solution, which I have told you. Now this is one important equation. Since ionic product of water is product of hydronium ion, hydroxyl ions, okay, and this is equals to 10⁻⁻14. Since experimentally we found out that concentration of H plus was 10⁻⁻7, and H plus concentration is equals to OH minus concentration. So if in this equation we take the negative logarithm on both the sides, we get negative logarithm. We get minus log of Kw is equals to minus log of H plus. Since it is in multiplication, on taking log it will add up. So minus log H plus minus log of OH minus is equals to minus log of 10⁻⁻14, which comes out to be 14. So minus log for minus log we write another term, that is P. So wherever minus log comes, we have to substitute it by writing P. So the equation now becomes pKw is equals to, and minus log of H plus as I've told you is pH. So we can also write as minus log as P, and it becomes pH. Minus log of hydroxyl ion becomes POH is equals to 14. So hence it becomes pKw is equals to pH plus POH is equals to 14.